In the intake section of the gas turbine engine, under the cruising conditions, the velocity is higher at the inlet, so the velocity has to be reduced, the Mach number has to be reduced, which results in increase of pressure. The pressure rise in the inlet section is termed as ram pressure. The efficiency of the intake section is usually determined using two parameters. One is the isentropic efficiency. The isentropic efficiency is calculated from the temperature difference. Second parameter is ram efficiency. It is calculated from the pressure difference. We can see the schematic for the ideal case and for the actual case. In the ideal case, the entropy will remain constant. The temperature and pressure will rise. Similarly, in the actual case, the temperature and static pressure rise, whereas the stagnation pressure is reduced and the stagnation temperature is constant. Due to non-isentropic conditions, the stagnation temperature remains constant, because due to friction effects, the internal energy and the temperature, static temperature is increased. The total temperature remains constant. So this is the formula for calculating the total temperature. In this formula, A is for the inlet section of the intake section, or the inlet of the intake section, and 1 is the exit of the intake section. So location 1 is before compressor, and location A is the free stream condition or the inlet of the intake section. This is the isentropic relation for pressure and temperature for the intake section, and this is the formula of the isentropic efficiency of the intake section. The relation can be written for the temperature difference, the ideal total temperature before compressor. It can be written in terms of isentropic efficiency. Using these two formulas, we can write the temperature difference, static temperature at inlet, and the ideal total temperature at the inlet. Ideal total temperature TO1 dash will be the temperature if the same pressure is achieved and the process is isentropic. Now we modify the relation. We can add and subtract TA in this formula. We will get the difference TO1 dash under ideal conditions subtracted by ambient conditions. So this can be replaced with this term. In terms of, we can bring the pressure ratio in terms of intake velocity, and then it can be converted using the specific heat relation in terms of gamma, and it can be written in terms of Mach number. Similarly, this is the formula for calculation of the temperature ratio stagnation to static in terms of inlet Mach number. Second parameter for determining the performance of the intake section is based on the calculation of pressure. So this is the pressure difference, stagnation pressure, stagnation actual pressure at the exit of the intake section subtracted by ambient pressure, and this is the actual pressure at the inlet of the intake section. So this will indicate the loss in pressure in the intake section. So both of these parameters can be used to predict the performance of the intake section. A typical value of intake efficiency is around 0.93. The intake efficiency can also depend on the location of the engine, and due to different locations the efficiency can change. The intake efficiency will be less for the supersonic intakes. We know that for the supersonic intake there are chances of the shock as the fluid enters through the intake section, or before intake there can be shocks which can result in pressure decrease. For the supersonic intakes we use a parameter based on the pressure or the total pressure. Since the ambient pressure is less, we can ignore the term PA. In that case the efficiency or the pressure recovery factor is PO1 divided by POA. For the supersonic intakes we often use the converging diverging duct so that the flow is subsonic after the intake section, because it is desirable to have the subsonic flow before the compressor section. So obviously the design of the supersonic inlet is more complicated due to the supersonic flow nature and the presence of the shock. From the experimental studies, the pressure difference due to shock in the inlet section can be estimated based on the free stream Mach number, and this formula is valid when Mach number is between 1 to 5. Another component or very important component of gas turbine is propelling nozzle. The purpose of the propelling nozzle is to provide high velocity jet so that the thrust can be produced. In the turbojet engine usually there is a single nozzle. In turbofan there are two nozzles, one is for the cold stream and one is for the high temperature stream. In the nozzle section sometimes afterburner is used. The purpose of afterburner is to increase the thrust by adding more fuel. The addition of fuel results in increase of temperature and increase of the thrust value. Now before the nozzle there can be other components after the turbine. These minor components are diffuser and jet pipe. So diffuser, the purpose of the diffuser is to streamline the flow after the turbine section. Jet pipe is to place the afterburner, and finally there is a nozzle. Usually the converging nozzle is used for the turbofan applications. The turbojet engine can sometimes utilize the converging diverging nozzle, but use of converging diverging nozzle has some issues. Due to this type of nozzle the weight is increased. Similarly length and diameter are increased, which is undesirable for the gas turbine for the jet applications. In addition to the weight and diameter and the dimensions, overall dimensions, sometimes the pressure is not very high, and when the fluid is expanded in the converging diverging nozzle the pressure reduces and the pressure is below atmospheric. So when the pressure is below atmospheric it can result in shock in the diverging section of the nozzle. Further, in case of converging nozzles we can place various components. One is the variable area. After the after burner we can place variable area, which is more convenient in case of converging nozzle. We can add the components for varying the outlet area conveniently when we are using the converging nozzle. Then we can also place thrust reverser in the converging nozzle. The purpose of thrust reverser is to change the direction of the thrust so that the speed of the airplane can be reduced. Similarly, sometimes noise suppressor is required. It can be more conveniently placed when the nozzle is of converging type rather than converging diverging. The noise is created due to high velocity stream when it exits the nozzle and mixes with the surrounding atmosphere. So purpose of the noise suppressor is to mix the fluid, mix various layers of the fluid so that proper mixing will result in more uniform distribution of the temperature. So better distribution, better mixing of the fluids at the nozzle exit will reduce the noise level. However, for the supersonic speeds we require the converging diverging nozzle, and it can be effectively utilized for the supersonic speed because the pressure is higher at the turbine exit as well as at the nozzle exit. So if the fluid is expanded in the converging diverging nozzle, the exit pressure is still higher than the surrounding pressure. In that case, the shock is not produced in the diverging section, and in such conditions the converging diverging nozzle can be utilized when there is highly supersonic flow. Similar to the intake section, we have efficiencies defined for the exit nozzle. One parameter is isentropic efficiency eta J, and second parameter is specific thrust coefficient. Specific thrust coefficient is the ratio of the actual specific gross thrust divided by the isentropic flow thrust. This is the gross thrust, momentum thrust plus pressure thrust. So this is calculated using the isentropic relation, and this thrust is calculated using the actual conditions. The ratio of 2 will give the specific thrust coefficient. Second one is isentropic efficiency of the jet nozzle. The efficiency of the jet nozzle is defined in terms of temperature. After modifying and using the isentropic relation for the nozzle section, PO4 dash divided by P5, PO4 divided by P5 dash equal to temperature ratio to the power gamma minus 1 over gamma. Similar relation which was used for the intake section. So if we use the isentropic relation in terms of pressure and temperature, and using this isentropic efficiency formula, we can derive this relation. This is the formula for determining the total temperature using the static temperature and velocity. Using relation between Cp and gamma, we can convert this formula in terms of Mach number. So we have three relations, 1, 2 and 3. Using these relations we can determine the exit pressure, and we can calculate the exit temperature as well. There are two possibilities for the exit section. The nozzle can be choked or it can be unchoked. If the nozzle is unchoked, that is Mach number at the nozzle exit is less than 1, then we will use these formulas for calculation of pressure, for calculation of the efficiency. or any other property which is unknown. Suppose we want to find the exit velocity. So exit velocity will be calculated using these general relations. But if the pressure is calculated and the pressure at the nozzle exit is higher than the ambient pressure, this means the nozzle is choked and Mach number is equal to 1. When Mach number is equal to 1, the equations are simplified. M5 will be equal to 1, and using this simplification we can convert our relations. This is the total temperature relation. Here M5 will be equal to 1, or MC critical Mach number will be 1. This is the formula for calculation of the ideal temperature at the exit. This is isentropic relation. So using these relations we can derive this relation. So if efficiency is known, we can find the critical pressure. We can find the pressure at the exit of the nozzle if we know the jet efficiency, the jet nozzle efficiency. These are the schematics. This is for the second case when the nozzle is choked. In such conditions, C5 will be equal to gamma R Tc, and this is the general case, or this is the case when the nozzle is unchoked. So here Mach number at the exit will not be equal to 1. Now our next topic is rocket propulsion. Previously we have considered the gas turbine engines, turbojet, turbofan, turboprop. These are basically air breathing engines. Rocket is a non-air breathing engine. It does not require the surrounding air for the combustion process and for generating the thrust. So rocket is a propulsive device that produces a thrust force for a vehicle as a reaction when exhaust mass is ejected with high velocity. So this is the definition of the rocket, but this is incomplete. For completion, rocket is a non-air breathing engine. So this will make difference between the rocket and the other engines, because it is a non-air breathing engine. So in case of rocket, the oxidizer as well as the fuel, both are inside the rocket region, both are on the port, and as they are non-air breathing, they can operate in vacuum space. When compared to the air breathing engines, we can list few advantages. First is thrust independent of speed and altitude, and large accelerations can be produced due to the shape and the design and the direction of the flight. They are capable of generating large accelerations. The thrust per frontal area, thrust per weight is largest when compared to other propulsion systems. The rockets are used for satellites, space flights, and other applications such as military applications. They are used for launch vehicles. The definition of launch vehicle: it is a carrier rocket, or it is a rocket to transfer, to carry, to transport the satellite or payload from Earth's surface to the outer space. It can be the so the launch vehicle is lifted from a launch pad, and it can be launched from sea at the submarine, or it can be launched within air. The launch vehicles are usually expendable. They are consumed. They are used only once. But there are examples. There have been research studies and actual studies in which the launch system is recovered and it is used for other flights. The consumable or expendable launch vehicles are separated from the payload, and they are disintegrated as they enter into the atmosphere. On the other hand, the reusable launch vehicles are recovered and they are used again. The rocket is used for spacecraft. Spacecraft is itself a vehicle which uses the rocket engine, and it is the vehicle which moves in the outer space, and these are the purposes, these are the applications for which the spacecrafts are used: for communications, earth observations, navigation and exploration. The components of spacecraft include a booster module and orbiting module, both of which can require the rocket engines, and the re-entry capsule. So if there is some staff or the crew within the spacecraft, so this is the only component which reaches the Earth's surface again. The booster module can be consumed, it can be abandoned, and it can be burned. The orbiting module remains in the space, whereas the capsule returns back to the Earth's surface. A similar vehicle is space probe. The purpose of space probe is to transport the robots in the Earth orbit and for the exploration purposes. Space shuttle is similar to spacecraft, but it is reusable, and almost all the components or majority of the components are reused. Again, the rocket engine is used in this type of shuttle, and this shuttle can move like a satellite, and it can return back like an airplane. So as I mentioned, the majority or many of the components are reusable in case of space shuttle. So space shuttle have advantage to carry satellites to the space, and the crews can travel for the repair of the satellite within the orbit. The rockets is used to send satellites. So satellite, as we know, it is the object which is intentionally placed into orbit, and there are several applications of satellite for the maps of the planetary surfaces and for other reasons such as the communication, navigation, and for predicting weather. Then satellites are the space station, and human spacecraft can also be considered as satellites. There are other types of rocket based on the purposes. One is booster rocket. The purpose of the booster rocket is to move the launch vehicle and to augment the space vehicle takeoff thrust. So this is the first stage usually, or one of the initial stages, so that the launch vehicle can move into the outer space. After booster top rocket, there is sustainer engine or a sustainer rocket. The purpose is to continue the motion once it has reached in the space region. The purpose of the sustainer rocket is to provide the further motion of the spacecraft. Now if the rocket engine has to be returned, if the space engine has to be returned, a retro rocket is used. The purpose of retro rocket is to provide the opposing thrust. When it provides the opposing thrust, the deceleration is caused, and it can move the engine back into the Earth atmosphere. Missile is also operated using the rocket engine and sometimes using jet engine. So missile is guided self-propelled flying weapon. The rockets are usually multi-stage, and the multi-staging is to continue the speed of the engine so that the vehicle can move into the outer space. So there are more than two or more than two stages, and in each stage there is an engine, there is a propellant, and there can be different types of staging. One is serial and other one is the parallel system. In the serial staging scheme, as it appears from the name, the rockets are in series. That is, one is at the bottom, then second one in the top region of the first one, then third one in the next top region of the second one, then it continues. So first there is a first stage or booster engines which cause the initial propulsion. When the booster engine run out of fuel, they are detached from the rest of the rocket, and then the second stage continues. Then after second stage, the third stage comes into action, and the velocity is increased through the third stage, and it is continued. The rockets can be of different types based on the driving force. There are chemical rockets and non-chemical rockets. Most of them are the chemical rockets due to the reliability, due to continuous power production. The non-chemical rockets can include electrical, thermal, solar and nuclear rockets. Some are used for the rocket applications, some are only in the testing phase. So chemical rockets are more common due to significant thrust for a longer duration, but there are many rockets which are based on the electric energy. The fuel in the chemical rocket system can be solid or it can be liquid. When solid propellants are used, both fuel and oxidizer are contained in the same casing or combustion chamber. So this is the casing or the region. The fuel and oxidizer both are in the same region. The propellant or the solid charge is in the grain form. There are particles of the solid fuel, and the particles consist of the chemical ingredients which can cause the combustion process. Once the combustion or ignition starts, the burning occurs at a smooth rate. The advantages of solid fuel is that there are no feed systems, there are no valves as they are present in the liquid units. The solid propellant rockets are relatively simple in construction because the components which are used for the liquid systems are absent in the solid fuel system, so it is more simpler. The example of solid fuel is gunpowder, which is a mixture of sulfur, charcoal and potassium nitrate. So sulfur and charcoal are fuels, whereas the potassium nitrate is the oxidizer. The advantage of solid fuel rockets is that the solid fuel can remain for a long time without any degradation. The limitation of solid propellants is that the performance of the solid fuel is relatively less. That is, the thrust produced is relatively less in case of solid fuel. These are various steps, various processes. Solid fuel oxidizer mixture is stored into the rocket. So this is the storage region, and there is a cylindrical hole in the middle. So there is initial combustion through an igniter. There is a cylindrical hole which is acting like a combustion chamber. So middle section is a combustion chamber, and due to the combustion process, the thermal energy, internal energy is increased, and the gases move through this nozzle with high velocity, and in the end we have the converging diverging nozzle. The liquid fuels are preferred in many of the applications. The reason is that the density is high. In case of liquids, the reason is that the solid fuel is in the grain form, and due to this granular shape, the overall density of the fuel is decreased. In comparison, the liquid fuels have greater density. So liquid rocket fuels require liquid hydrogen or hydrocarbon. These are fuels, and a liquid oxidizer, which is liquid oxygen. So this is fuel and this is oxidizer. So there is a pump for moving the oxidizer, and there is a pump for moving the fuel, and this is the combustion chamber. The combustion results in high velocity exhaust gas, and we get the supersonic flow at the exit of the converging diverging nozzle. And this is the pressure value within the pressure vessels of the fuel and oxidizer. About 55 maximum or typical pressure up to the 5.5 megapascal, and as the fuel expands, the temperature reaches up to 4000 Kelvin. After the combustion process, this is the temperature which is achieved.